This presentation is going to cover NoSQL concept for the relational DBA, which I'll kind of introduce the topic here in a few slides. I think is relevant for certainly most of the folks that I talk with. Now, in an effort of being overly scripted, right, and getting some eye rolls from the room, I like to start all of my presentations with a story and then a quote. And there's three numbers that kind of tell the story that we're going to discuss today. And 40, it was kind of interesting, and this number, by the way, is changing every time I look at the site, but 40 is actually the number of NoSQL platforms when you look at the Wikipedia page. Right, I know Wikipedia isn't exactly a scholastic journal, but I think it does help us put in perspective just the breadth of this market and the complexity that when we hear NoSQL, we actually have to face. 13 years ago is technically when this NoSQL movement started, right? Initially kind of some fairly forward-thinking developers at Facebook and Yahoo, kind of understanding that the relational model didn't work for their specific use cases and kind of starting us on this journey. And I just like to bring this up. I often think of NoSQL non-relational as a fairly new concept, and it really isn't. 13 years in technology is almost a lifetime. Now, what is kind of new is, and what I think puts us in this room is enterprise IT, right, really starting to adopt many of these technologies. Right? For the Facebooks of the world, they built it themselves and they drive their business on it, but now the folks that I typically talk to, right, DBAs and IT infrastructures, really starting to embrace and bring these technologies into their environment. So that is a relatively new concept, and honestly, I think why we're in the room today. And then finally, I've got 45 minutes to talk to you today. Hopefully, I'll be able to fill that time with content you find relevant, but let's go ahead and move on. The quote I like to tell, it's from Gavin Belson. Those of you that have seen the show might laugh, but it really was a relevant concept. I've been in data management for a long time now, and this show, I think, has a nice satirical edge on a lot of the things that I deal with every day. But the quote is all about data creation is exploding. With all the selfies and useless files people refuse to delete, the world's data storage capacity will be overtaken. Data shortages, data rationing, data black markets, data getting, right? No secret to anybody in the room, data volumes are expanding well beyond what we ever thought possible. We actually co-sponsored a survey with DBTA at the very end of last year, and we talked on a number of topics with our customer base and our prospects. And this kind of shows the scale at which volume data is growing. The left represents the left represents non-relational technologies, the right representing relational. And you can see the vast majority of our respondents are seeing their data volumes grow annually between 10 and 50%. Right? And these are a lot of large organizations managing terabytes to petabytes of data. So even 10% at that scale is pretty impressive and certainly introduces some challenges that our customers have to face. So who am I? You heard the introduction, a little bit more context. I'm a system consultant at Quest Software. Quest is a company that provides management tools for IT administrators. And I think that gives me a unique perspective, I at least hope, in really how Quest has to embrace these new technologies. We can't be too early, right? If we're too early to market with tooling, there's no users out there that actually need them. If we're too late, some competitor has snatched up our market, and now we're trying to play catch up. So we really have to kind of time the market for tooling for non-relational admins to help them manage their infrastructure, and that's kind of where I think, I hope that I have an interesting perspective, at least on how our customers are solving some of the challenges that they face. So I started working with relational systems in the early 2000s, and it's really been within the last, I'd say, 18 months that I've started honestly having more conversations about non-relational technologies than relational with our customers. All right, so I think the timing here is good to really kind of move on this journey. Definitely would love to converse with you through whatever social media forum you love or use. I'll also be at the Quest booth for the rest of the conference if you guys do want to stop by and chat. So effectively the topic today, excuse me, we're going to work on kind of translating concepts, many of which will be very familiar to those with a relational background, into their non-relational counterparts. Right, and this is how I learn. I'm not sure if all of you learn this way too, but it's the best way that I learn is to think about something that I know really well and then try to translate it into something that I don't know. And through that translation, I can kind of better internalize what these things mean. While we do that, we'll discuss some of the challenges that non-relational systems were built to overcome and actually how they then overcome them. And honestly, my objective, if I had one singular goal of this session when I've presented it, is to really build confidence amongst those with a relational background that non-relational systems are good fits for certain types of use cases. Right? I hate when I walk into an IT shop and they say, you know what, the reason we haven't implemented MongoDB across any of our systems is because we don't have staff to manage it. Right? So really what my goal is of this presentation is taking those existing DBAs, right? Oracle DBAs for the last 25 years, right? And trying to build confidence that non-relational technologies are not technologies that we should just simply say, you know what, I don't want to deal with that, it's too different, right? That's really my objective. Definition-wise, I think NoSQL is worth just kind of level setting the audience on, because it's one of those, there's a lot of these, but I always say it's kind of one of the most misused terms in IT. And the problem is the definition has changed over time. But you know, when NoSQL was first kind of formulated, it was actually NoSQL, right? We do not use SQL to actually work with these database systems. Many of the folks at Cassandra, or DataStax and their use of Cassandra kind of shifted the definition very accurately. They now call it not only SQL, right? Because the fact of the matter is, and one of the things we'll be discussing today, is that you can actually use SQL to interact with non-relational systems. But it's not the only way that you can. But even that definition has kind of become a little bit archaic. There's a really good definition, named Guy Harrison. I've got a reference slide at the end if you want to take note of it. Wrote a book called Next Generation Databases. And he defines it as just more of a general, wide-sweeping, NoSQL systems kind of reject many of the constraints of the relational model. Right? And that's really, I think, the best way to internalize this. There's so many NoSQL systems, and each of them kind of has differences in how it works. But at the end of the day, NoSQL systems reject many of the fundamental concepts that relational systems were built on top of. All right, this is that slide just to kind of show you the 40 number that I threw out during our story. Honestly, I took the screenshot a month ago, so it's probably even changed since then. But this is Wikipedia's listing of NoSQL platforms. There's some that I know of that aren't on this list, so 40 is probably even a low mark. And even then, you see there's 9 different categories of NoSQL systems. Right? So if we even just try to focus on those 9 categories, it becomes really cumbersome and difficult to wrap your head around. Now, for the sake of time, again, we've got 45 minutes. Many of the use cases we touch on today, I'm going to focus around Cassandra and MongoDB. These are the two that I see most often out in the market. There's a few others I probably would have included if this was an hour-and-a-half session. But I think Cassandra and Mongo do a good job of talking through some of these concepts in 2 different perspectives. And then a lot of the concepts, even if you're not a Cassandra or a Mongo person, you can kind of translate them into whatever platforms you might be managing. Now, a way to kind of generalize Mongo and Cassandra, though, and this is even a good way to think about a lot of non-relational systems, is that they are distributed databases, right? We have lots of different servers, nodes, whatever you want to call them, working together to support the data storage needs of a specific application. If you look up a proper definition, MongoDB, it's a documented-oriented database. It stores data in documents. We'll talk through a little bit about what that is in a bit. And Cassandra I refer to as a wide column store database. All right, so data is kind of organized, instead of into rows, it's organized into columns, and that kind of shifts the way we have to think about how that data is managed. Now, Mongo and Cassandra, again, these are the 2 that we're going to talk mostly about today. Why do they even exist in the first place? And again, it's all about rejecting the constraints of the typical relational model. And what kind of brought on this movement was, and big data I put in quotes because that's one of those other most misused terms in IT. But the fact of the matter is, our data requirements outgrew what we could store in a single table. Right? And that's kind of the best way to think of why do we need non-relational systems, is because when a table gets to be billions and trillions of records deep, we can't efficiently manage it anymore. Right? No matter how fast our disks are and how much memory we have, to scan through 5 trillion records of data is just unmanageable. So that's really why these kind of systems occur. And you know, joins get complex in that model. In order to split data between different servers, relational systems make that very difficult, in many ways impossible. And availability in a lot of relational systems, yeah, there's a lot of ways to do it. I'm not going to stand here and say you can't gain 5 nines availability on a relational system, but that typically comes with extreme cost, lots of complexity in order to make that happen. So a lot of these non-relational systems were kind of built with availability at the forefront of what they want to offer. So as far as an agenda today, kind of what are the different pieces of this journey we're going to talk through? We'll start with some concepts around schema design and querying. Right? How do we store data, and then how do we get to it? We'll then look about availability and consistency and how those work in the non-relational model, again, kind of translating back to what we're used to in the relational world. Thirdly, we'll talk about horizontal scaling. Right? How do we get that data out of one table into a way that we can efficiently manage it scalably? And then lastly, we'll kind of talk about making the move. I know that's kind of the theme of this track at the conference. So, those of us that are in IT organizations looking to make this move, what are some of the things we need to consider to actually take care of that? All right, so we'll start here with schema design and querying. And we'll start with Mongo, and you'll kind of see the trajectory that we're going through here. We'll talk about kind of Mongo, Cassandra, document databases columnar. And kind of use that to form our translation. So MongoDB, and this applies to other document and oriented databases too, CouchDB, DocumentDB, CosmosDB, they kind of store data in documents instead of tables, right? We're familiar with tables where we've got rows and columns. When I talk to my friends who are not in IT about what I do, I just say it's like a big Excel spreadsheet, right? In that whole kind of tabular approach. Now in a document, JSON is a very common form of a document. Instead of having rows, you have fields, right? You get these brackets that define a JSON document, and then inside of the document, you've got field names, and then you've got values. I should be using my laser pointer. Sorry for those on that side of the room. I'll point over here. Maybe. There we go. So if I had the most basic form of a document, right? Myself in a tabular world, I'd look like this. In a document world, pretty similar. Right? Not a whole lot of advantages or disadvantages to either or in this simplistic operation, but that's kind of what a document would look like. Now, a lot of the benefit from MongoDB and other document-oriented databases is that what we can store in a document is extremely flexible. Right? We can have single values. Right? That's that example I just talked through. Field, value. But we can also have arrays of documents, right? We don't have to predefine how many columns or how many values I'm going to stuff inside of a single field. Right? In a table, I kind of do, right? We have a certain number of columns that we set up in our schema, and if I want to store more things, I've got to go back and add columns to support that. Right? In a document, I can have arrays, kind of an unbounded list of items. We can also store documents inside of other documents, right? Often referred to as nested documents. So I might have one field that I want to map to another document. We could have multiple layers if I need to. And it just lends to a very flexible way to store data. Now just terminology-wise, documents in MongoDB, they're organized into collections. Collection is just a logical container of documents. Collections are then organized into databases. Right? So when you hear of a MongoDB database, it's talking about a group of collections. A group of collections will be storing documents. Now, just to kind of show you some of these properties in action, we've got a slightly more advanced document here, where again, you've got some ID value and then myself as a first name, last name. But here, the address field you can see is a nested document, where inside of that one document, I've got a city and a state. All right, and we could, of course, have a address to line, a postal code, right? We could stuff as much as we want in this nested document. And then down here, I've got an array, right, of my siblings. My brother and sister will be very pleased that I'm talking about them. But you can see siblings here is an unbounded array. I've got 2 members here, but this could have as many as I wanted. Right? In the relational world, I really need to use 2 different tables for this. Right? I'd have a primary table of myself, and I could almost like unwrap that nested document into multiple columns, right? City, state, however many I needed. And then if I wanted to do this array down here of siblings, I could do it via columns, but then I'd have to know ahead of time how many columns I needed. Right? So what I would do in a relational world is I'd create a second table with some kind of foreign key linking these 2 together, and then list out, right, my siblings. So Jason has siblings of Kevin and Melody. Right? And that's okay. This is a really basic example, so this use case will be fine in the relational world. But as this use case starts to get more complex, you can see how this can start to become difficult to manage. So kind of the advantages of this document model, right? First of all, these documents can get very large, and that's a little scary at first, right? We could have one document with hundreds of fields, multiple layers of nested collections, unbounded arrays inside of it, but that's actually an advantage. Because if I can stuff all the data I need into one document, it gets really easy to go and fetch that data. Right? And I don't have to do big expensive joins between multiple tables in order to fetch the data that I need, like who's the oldest sibling of Jason. Right? The other real nice advantage of documents is that the schemas do not have to be well defined ahead of time. You'll often hear schemaless when talking about something like MongoDB. The folks at Mongo hate that because you can define schemas, right? You can, and actually Mongo calls them validators. You can say this document has to follow this structure, and now you have a well-defined schema. But you don't have to. So they'll often call them dynamic or flexible schemas. You don't have to decide ahead of time what your data is going to look like. You're going to start throwing documents together. And if a year after you deployed the application, you want to go into a new country that has a different format of addresses, right? Different ways that they do, locations, just start storing that new data in that document. There's no reason two different documents in the same collection have to have the same data inside of them. That's a little scary when you think about consistency of data, but it's not a requirement, right? So it's a really nice option with these flexible documents. You also, when you make these modifications, you don't have to go back and update old data. This is one of the biggest challenges with large relational tables. If you decide you want to add a column to a trillion row table, you've got to decide to do with those trillion records. Do we null it out? Do we add some default value? Right? And those schema changes can get really big and complex. Right? Now, how do we actually query this data in Mongo? They provide built-in functions, right? So this is one of, honestly, it almost seems trivial, but we've been so used to querying data using SQL. It's such a well-established language. It's one of the first programming languages, if you could even call it that, I learned in college, right? Select star from table. And Mongo's different. So that's a little scary to a lot of relational folks. But the fact of the matter is the same concepts apply. We're just translating languages, right? So typically in a relational world, we can write a select star from people where first name equals JSON, right? I can pull all the data related to JSON. In Mongo, that's very similar. You're just running a find command, right? And that first name colon JSON, that's a pattern match that we apply to this find command, which is almost like the equivalent of a where clause. It's a pretty straightforward. Again, it's not SQL, but we're fetching data by applying clauses to our find command that go and fetch, matches to certain patterns. And we can use operators in those conditions, right? So select star where first name equals or, right? There's an or operator that we pass into the find command that just specifies two different patterns. Right, so the query language on Mongo, very powerful. Yes, it's not SQL, but uses a lot of the same concepts in order to pull out and extract data. Now there is a way to do, I call it SQL-like querying in Mongo. Mongo calls it their BI connector. This is not free. Mongo as a platform, of course, is open source, but the BI connector is a paid offering. But for those companies using MongoDB that really need to provide SQL-like querying, a lot of times this will happen to, that's why it's called BI connector, out to a BI interface, or we've got business analysts who just really like writing select star from table. This BI connector will do some of that translation for them and return the data not in documents but in tables. Right, so it's almost like a workaround to doing things the Mongo way, but it's a nice option for customers that might need it. Now, again, kind of a summary of MongoDB in terms of schema and querying. There's a lot of really nice benefits here to this model. I was afraid of it when I started. I'm not gonna lie. It was different, and I was like, where are my comfortable tables that I can join together and do whatever I need to? But the fact of the matter is, it's very hard to find a data model that does not fit into this document structure. Right? It's almost impossible to come up with a data model where you can just say this doesn't fit. It's different, but it fits. Another really nice thing here is if you properly define your MongoDB data model. I've seen some customers who try to do a one-to-one relationship between tables and collections, right? Where they say, I'm just going to take this relational table and build a collection off of it. And you end up with lots of different collections, right? One-to-one for each table. And that's not really the way MongoDB was designed, right? Part of the purpose of this data model is to eliminate the need to join stuff together. Right? I like to be able to go to one collection and one document to find all the data that you need. So if you do a really good job at your data design in MongoDB, you can eliminate that need to do costly join and lookup operators. Right? And again, these flexible dynamic data models allow for very rapid, very agile changes without the need to go back and modify legacy schemas. So you talk about agile development, DevOps, continuous integration, continuous deployment. This fits perfectly for that, right? Schema changes can just happen on the fly. You decide to store a different type of data, and you do it, right? You worry about the old data later. Right. Now there are some disadvantages. In my college course on data design, it was beaten into us about heavily normalized data, right? We took, on our final exam, they'd give us this mess of relational tables, and they said normalize it, right? That was the way to do it. Well, in Mongo, denormalized data is a good thing, right? Or in many ways it is, right? The nesting of data inside of documents really lends itself to denormalized data. And that's something you do have to consider when building out an application, right? If I've got the same document in 10 different places, I better make sure that I'm updating it every time I store it in. Flexible schemas can also be a challenge in data consistency, right? If your application expects every user to have the same exact data present in its document, that's a couple extra steps to get there in Mongo, right? You have to use those validators I talked about to ensure those schemas, and then there's added complexity and overhead there. So you really need to code the application to be okay with different types of data. Right? And then the querying's different, but again, it's usually fairly comfortable. It doesn't take a lot of training to get to a level of comfort in Mongo querying. Now in Cassandra, the Cassandra data model is different. It's non-relational, again, they often get lumped together, but it's a very different method of storing data. In Cassandra, it was kind of started as a column-oriented database, because instead of thinking in data in rows, we think of it in columns. Right? And I'm going to store all columns together. Multiple columns in the same row may not be together, but that's okay, because we're going to keep all the same type of data, the same column, in the same location. Columns are linked by a key. Think of it like a primary key, that makes sense. And then columns are grouped together into column families, and they use that term to kind of make it feel like a table, right? A column family is a group of columns linked by a row key, and if you were to see a picture of it, it'd look like a table. All right, so this data actually looks a lot more familiar to relational DBAs, but there's a lot of nuances there that become important. And again, this is right from the Cassandra documentation, right? This is what a Cassandra column family looks like. You've got multiple columns here. This is a row key, John Lennon. He's got multiple columns associated with it, but from a storage perspective, what's actually grouped together are these columns. Is there a question? I'll take it quickly.
So, are these columns then distributed?
They are, and I've got a slide where I'll kind of talk about how data flows through in a second, yeah. So again, Cassandra kind of looks relational, but it's not, right? And we'll talk about what I mean there. Now, Cassandra, when it first came out as an open source platform, as part of the Apache project, all the querying and coding was Java. Right, again, this was really uncomfortable for relational folks who really like their SQL querying. But DataStax kind of led an initiative called CQL. This is 6-7 years ago. If anybody from DataStax in the room, feel free to correct me. And CQL, Cassandra Query Language, built in this familiar, comfortable query language as part of the Cassandra platform. So CQL is fairly well supported. There are still a few things you can't do with CQL, but most of what we would expect to be able to do with data can be accomplished here. Creating a table, pretty simple. Querying of data, select statements, inserting data with insert statements. So if you're getting started with Cassandra and you're a relational person, just make sure you look up CQL. You'll feel right at home. Right? So some advantages are specifically that. Right? Cassandra looks a lot like a relational system, from the data storage to how we model data to how we query for data. They're a little bit more flexible than relational counterparts. One thing I think I had on the slide, I'm not sure I said it, but was that row keys don't have to have the same number of columns. Right? Data is organized columnally, so I don't need those artists, John Lennon. If I don't need to have his country of origin, then I don't need to store it. Right? It's almost like a null column in a relational table, but there is still some overhead and some storage associated with null data. In Cassandra column families, I don't need that. Right? We don't have to have the same number of columns. Some disadvantages of this data model, though, sometimes this comfortability with relational systems can actually get people in trouble, specifically from a performance perspective. Because we're writing select statements thinking that what's happening behind the scenes there is what I would expect it to do in Oracle or SQL Server, and it's not. And this is specifically true when we do things like select star, right? Or select multiple columns in the event that maybe I need it, but I don't really. I'll talk about why that's inefficient here in a minute, but table scans and column scans can get really expensive in Cassandra, and I might think if I'm thinking this is relational, that's not going to be a big deal. So those are kind of some of the data model concepts that become interesting here. I'm kind of stitching that together now into availability and consistency. CAP theorem, very well established data management principle. Don't remember exactly when this was formatted, but basically the premise of the CAP theorem is that you have three sides of the triangle. You have availability on the top, partition tolerance on the bottom, consistency on the left. And it basically says in any data management system, you can have two of the three. You can't have all three. All right. There's been some kind of shifts to the thinking here that you can kind of have the third, but you're always going to favor two of the three sides of this triangle. And this image, pretty easy to find online, just kind of tells you where some of the systems we think of fit in. Availability, of course, relates to uptime, 100% uptime. Consistency refers to the effectively the read consistency of data, right? If you write a row and then read it at the same time right after, are you always going to get that newly written data? And then partition tolerance is if you get separated network-wise from the database infrastructure, can you continue to operate? Relational databases really fit on the CA side of that triangle, right? They value consistency and availability over partition tolerance. Right? There's lots of ways in a relational system that you can keep a system available. Oracle's got racks, SQL Server's got always on, DB2 has pure scale and partitioning. There are lots of ways to keep relational systems up in the event of a failure. And really, relational systems were built on the backbone of strict transactional consistency, right? ACID compliant transactions. That's almost a fundamental what a relation system is built to do. But a lot of relational systems struggle with partition tolerance. Right? In rack, you've got a single source of data. You have a network partition between your rack node and the data, you're gone. Right? SQL Server, always on, you've only got one read-write replica of those databases. Yes, you can read from a secondary replica, but if you need to write data and you're separate from the primary node, you're offline. Right? So that partition tolerance is what relational databases often struggle with. Now, MongoDB takes a different approach. Right? MongoDB has consistency and partition tolerance, but not 100% availability. Right, the MongoDB architecture is built on the backbone of what they call a replica set. This comes from some MongoDB documentation. But you basically have an application connecting to a primary member of a replica set and then replicating out to as many second members as you want. But only one node of that replica set can accept read-write transactions. Right, these other nodes are at worst are offline, just there for failover. At best, you can run read queries against them. But there's one source of read-write transactions inside of a MongoDB replica set. And what that means is if your primary goes down, there is a failover process that does come with some downtime. It can be very quick, but the fact of the matter is there is downtime when a failover occurs and a new primary needs to be elected. So with Mongo, you get really highly consistent data just because there's only one place you're writing the data to. And you have partition tolerance because we can stay connected to these replica sets, but you do not have no downtime failover. In Cassandra, you have partition tolerance and availability, but you lack or lose a little bit of consistency. All right, in Cassandra, to your question earlier about where does the data go, Cassandra is built on this architecture. It's often referred to as a ring. You'll even see if you talk to the DataStax folks, a lot of their UI is kind of built around this ring of nodes. And every single one of these nodes is available for read-write activity. Right? You can read from any of them, you can write to any of them. And so in the event of a singular node going down, in Cassandra world, that's okay, because any of the other nodes can just start accepting that data. There's not even really a failover per se. It's just we connect to a new node and we're off and running. Now, when you write data to a node, it's then going to get replicated out across as many nodes as you want it to. Cassandra calls that a replication factor. So let's just use a round numbers. You have a 10-node Cassandra ring, or cluster as is often called. Your replication factor is 3. That means if you write data to one node, it's going to get replicated out to 3 other nodes. So theoretically, 2 of them can go down and you still have access to read the data that was written. Now, kind of the way that data gets distributed around these nodes is those column families get split node to node. Right? So they're not stored together per se. They could be if you want them to be. But column families are written to an initial node and then replicated out. If you connect to a node to read data that's not here, it'll go and get it. right? So there's some latency that might occur there if the data that you're reading isn't on the node that you're on, but the fact is it can still read any data that's a part of the cluster, assuming that it's available at least in accordance with your replication factor. So because of that, Cassandra is highly partition tolerant, as long as there's a node that you can continue to connect to, and as long as the servers that are down are less than your replication factor, right? In other words, all of the replicated members are down, then partition tolerance is fine, and availability is fine too. Because again, as many servers can go down, as long as it doesn't exceed your replication factor, you're generally okay in Cassandra. But consistency can be a challenge, because any of these can accept write requests, right? How do you handle two users connected to different nodes reading the same data, or writing the same data and reading the same data? That's one of the sacrifices you make in Cassandra. There are lots of ways they can overcome that. If you talk to the DataStax folk, I'm sure they'll love to talk to you about them. But in the core Cassandra engine, they value partition tolerance and availability over consistency. So fact of the matter is, this is, again, a little bit of a challenge when we talk to relational folks who are so used to valuing consistent, highly consistent data that I can keep up as long as I have the infrastructure and the money to maintain the level of availability I need. In the non-relational world, we're going to value other parts of that CAP theorem. So if you're looking to choose a platform, and I know a lot of these decisions are made way before IT administrators get the chance to put their thoughts forward, but if you are a part of the decision process, what non-relational technology might we want to explore? CAP theorem is a good thing to understand, and just think about those three sides. What's most important to us in our business, and whatever's least important in the list, that'll kind of help you decide your process. Right. And this is a good, just going back a slide again, if you Google CAP theorem, this will come up right away. The slides are available, they're already available, but if you go to the DBTA site for the summit, the slides are available. This is kind of a good, just to kind of see what are the types of non-relational systems and where do they fit in the theorem. All right, so kind of continuing, scalability. All right. Now, non-relational systems are not the only way we can scale data, of course, right? We've been scaling database servers for dozens of years without this non-relational concept. I usually summarize ways to improve performance. There are three ways. All right. If I have a database server that's running slow, how do I improve it? The first way is tuning and application design, right? We sometimes forget about that because we're so used to throwing hardware resources at a system that we just forget, oh yeah, maybe I can actually look and tune this query or build an index or redesign the application around how data's cached and where data's stored. But that's always going to be, in my opinion, the best way to improve performance, right? Let's have a well-tuned, efficient application that can run on as little hardware as possible. Beyond that, we've always had the ability to vertically scale a database server, right? Vertical scaling, basically that throwing hardware at a system. Right, let's take my one SQL Server instance, and if it's slow, let's just add some memory to it. And if it's still slow, let's add some CPU. And if it's still slow, let's move its data files to all flash disk arrays. And at the end of that process, it's probably faster. Is it fast enough? Maybe. Now vertical scaling is a good option. It's an easy option, but it's extremely expensive. And the more cloud starts to infiltrate our environments, it gets even more expensive. If you've ever gone onto Azure and spun up a Windows VM and looked at the billing profiles for some of those high-scale systems, it's ridiculous. Like $10,000 a month, right, for a 8 CPU server with like 128 gigs of RAM. So vertical scaling, really, really expensive. So horizontal scaling, right, that's a third option. Now, we could horizontally scale with the relational systems. Right? I'm not going to stand here and tell you that you can't do this with Oracle or MySQL or SQL Server. But the fact of the matter is, it's really, really hard. Right? There's kind of a halfway point here that most relational systems have around table partitioning. That allows you to take one table and split it amongst multiple disks. So that's a good option for balancing I/O, but you still have that data living on a single server. Right? Now, what happens, again, this is one of those fundamental concepts we talked about at the very beginning of the presentation. Big data, I generally refer to it as when I can't store data efficiently in a single table. Right? That's big data to me. So when that happens, one of the things, horizontal scaling basically means let's take this data, this one table, and split it between multiple servers. Again, you can do that in a relational model. It's just very hard. The application logic is going to have to determine where to write data and where to read data. Balancing that data over time gets really difficult. I think Oracle, even in some of their latest versions, has some automated sharding. I just think it's really, really hard in a relational model. Right? These non-relational systems were really built to offer horizontal scaling as a core fundamental technology inside of their platforms. The way that Mongo hands it, we talked about these replica sets earlier. Replica sets are designed to offer availability, but to scale MongoDB, you build sharded clusters. And effectively, the core, we talked about shards, think of this as one collection, or table, split between multiple shards. Now in a MongoDB, a proper MongoDB architecture, there we go, each shard is likely also going to be a replica set. So this is where you can kind of offer both availability and scaling in a single deployment. So each of these shards, if you think about a table with like last names in it, right? One might contain A through H, the next is H through M, the next is M through Z. And then you've got these Mongo S systems, which is what they refer to them as querying servers. So your users connect to a Mongo S. The Mongo S contains the logic that splits the data. Mongo calls them chunks. Right? So basically where each chunk of data is and on what node. And then MongoDB takes care of, all right, you need this data, I'm going to go to this shard to go and get it. Right? So that's how MongoDB handles shard. It's very graceful. If you take any of the online Mongo courses, you can set up a sharded cluster in just a few minutes. Right? And if you translate to how you would even think through that in a relational model, it's pretty eye-opening, right? How native that is to the platform. So again, very simple. Now this does increase the cost of a MongoDB deployment, right? Sharding, where you're talking about adding nodes, yes, this increases your infrastructure, it increases your cost. But the nice thing is by sharding horizontally instead of vertically, it's usually a lot less of a cost, right? If you look at the Azure cost of a 2 CPU, 8 gig of RAM server, and maybe 10 of them versus one larger scale template, it's much lower cost. So scaling horizontally in many cases, even if you have more infrastructure, you have more servers, it's a much cheaper way to scale a system. Now again, Cassandra, honestly, the fundamental, like how it works is very different from Mongo, but the core concept is pretty similar, right? Data is sharded, different column families or different columns sit on different nodes of your ring, so that if you're going and querying subsets of data, you don't have to go to the entire cluster, you don't have to go to the entire table. Cassandra handles, they call it a mem table, handles kind of, all right, you need this data, I need to go to this level of the ring to go and get it. And because the data can be replicated out to different nodes, you might not have to go to that many of them to get the data that you're requesting. Right? So again, adding nodes to a Cassandra cluster, they will really advertise that Cassandra is one of the best systems at scaling linearly. Right? So for each node that you add, you get a linear proportional increase in performance. Right? And they've got a lot of benchmarks that kind of display that. A couple things about Cassandra. Higher replication factors will increase write overhead. Right? The more data you have to write out to, the longer those writes might take. They will result in faster reads. Right? If you have a 4-node cluster where you're writing data to all 4 nodes, right? Your replication factor is 4. That will lead to faster reads, right? If the data that I need is always on the node that I'm connected to, it's going to be very fast. If the data I need is not on the node that I'm connecting to, it will be slower, right, based on your network latency. So higher replication factors, more consistent data, more data availability, very fast reads, more backend storage. Lower replication factors are almost the opposite, right? So this is often a balancing act, and honestly, it's one thing I see, especially in the design process of building out Cassandra clusters, that you really want to spend some time on, right? Is think about what's most important between these items and then build a replication factor either high or low, depending on what your goals and priorities are. So again, relational systems, traditionally, horizontal scaling is really, really hard, right? I'm not going to say it's impossible, but it involves a lot of application design, it involves a lot of complexity, and it's something that you're going to constantly have to babysit, all right? In these non-relational models, it's so native to the platform, you can tell they were really built with scaling as a day one feature, and because of that, not only is it simple to implement, for the most part, it's a lot of set it and forget it too, right? You can be confident that your data's scaling, and adding nodes is a fairly trivial process. So last thing I want to cover, right? Making the move, and when I was building out this deck, I thought, all right, the theme of this track is making the move from non-relational to relational. All right, and I was like, wouldn't it be cool if the summary of this was, here's one button you could push, and all of a sudden your SQL Server data is in MongoDB. You can't do that, right? No matter, some vendors will kind of advertise that, but it's really difficult. You can do that poorly, right? There's a lot of systems that will say, here's my, and I even talked about this in Mongo earlier, where if you do a one-to-one mapping between tables and collections, you can get data from relational into non-relational really easily. But that's not really the purpose of these non-relational systems. So honestly, this move is hard, and in many cases, it's impossible. Most non-relational deployments that are brought into an enterprise are brought in with new projects, new initiatives, new applications. Right? For these types of use cases, you're almost waiting for those relational systems to age themselves out, so where you can bring in their non-relational counterparts. So what I talk to a lot of customers about making the move, and actually this is an interesting point down here, the more you see JSON data, this is almost becoming a ubiquitous standard in the industry that does make this move a little easier. Right? Microsoft announced JSON support in SQL Server. There's similar support in most non-relational platforms. So if data is universally stored in JSON, it's easier to move between systems, but again, there's data model challenges there that you really don't want to do a one-to-one. If somebody offers you a one-click migration from relational to non-relational, don't do it. It's defeating the purpose of non-relational systems. So really, how does this move happen in enterprise IT? I usually tell customers, really it's about a skill set move than anything else. Right? This sounds a little corny, but that really is. The customers that are successful with non-relational projects are those that embrace non-relational. They don't try to fit non-relational technologies into their relational bucket and just hope that it works. Right? So whether that's a singular DBA who's been managing relational systems for 20 years and now just says, you know what, I'm going to jump into non-relational and attack it and understand what it's good for and understand what it was built for, they're going to have a really good and positive experience. If it's the relational DBA who's more concerned about job security and losing their Oracle deployment because once it moves off of Oracle, what am I going to do? Those systems are either going to hire new people or their non-relational projects are just going to fail. Because we have to think, in a non-relational world, we have to think about how do I monitor availability and why is that different relational to non-relational? Right? How do I performance tune a non-relational system? Do I performance tune a non-relational system or do I just add nodes? Right? So really, again, my purpose of today's session was not to give you a one-click easy button for migrating relational systems to non-relational. It was to kind of talk through some of the challenges and concepts that non-relational systems were built on top of, and hopefully have everybody here walk out of this room saying, you know what, yeah, there's advantages and disadvantages to non-relational, but I'm a DBA, I manage databases, and this is all just data, right? So hopefully we've accomplished that goal. There's several resources that I leaned on very heavily to build out this content. Both MongoDB and DataStax offer tremendous free training on these platforms. And honestly, most of what I learned to build out this deck was through this free training, right? My company would have gladly paid for me to go, but they were very happy that I could do it for free. So absolutely sign up for these. They're self-paced, there's labs, there's examples. If you like learning by doing, these are very, very good ways to learn these platforms. And then I can't mention enough, I very rarely pull out books off my bookshelf. My wife always makes fun of me because I have this massive bookshelf in my office with dozens of books, most of which were given to me, sitting there. And literally the only one I think I've pulled out in the last 3 years is this book by Guy Harrison. Anytime I want to look up a new database platform, he does a really good job at the end explaining, he's got about probably 80 non-relational platforms. And with each one, he's got a section. What is it good for? What is it bad for? What's my take? So if you haven't read that book and you're kind of trying to figure out, where do these non-relational systems fit in, it's a really, really good one. I couldn't recommend it enough. Great. So I hope that was valuable. I'm going to be around for the rest of the conference if anybody wants to chat further, but I appreciate you guys' time today. Punctual.